Alright, so now I'm going to talk about the secant method. So this is a slight variant of the Newton method, where you avoid the need for computing the derivative of the function. So you avoid the need to know f prime at x. Okay, and what you do is you approximate the tangent line by the secant line. So let me give you an illustration of this. This is f of x. Let's just say this is alpha n, right? So that would be the tangent, right? So the slope of the tangent line is equal to just f prime at alpha n. And then you could have a previous iterate alpha n minus 1, and you could have the secant line connecting and take those 2 points. Right, so this is the tangent, and then this is the secant, which has a slope which is equal to f at alpha n minus f at alpha n minus 1 divided by alpha n minus 1. All right, so, and then if alpha n and alpha n minus 1 are close enough together, then the the slope is well approximated, or the slope of the secant line approximates the derivative of the function. Right? In fact, that's, if you recall, that's how we define the derivative of a sort of continuous function using limits, basically. Right? So anyway, so f prime at alpha n is approximately equal to f at alpha n minus f alpha n minus 1 over alpha n minus 1. Okay, so if you compare the Newton method, right, so Newton's method says that the iteration is saying that alpha n plus 1 is equal to alpha n minus f of alpha n divided by f prime of alpha n. All right, so as you might expect, the secant method is very similar, except that every time you see the derivative, you replace it by this secant approximation. So alpha n plus 1 is equal to alpha n minus f alpha n, and then f alpha n minus f alpha n minus 1 divided by alpha n minus 1, sort of reciprocal. Okay, so all right, so that's the Newton method and that's the secant method, and the remark is that you need 2 starting points, 2 starting values. So you need an alpha 0 and alpha 1, right? And then once you have alpha 0 and alpha 1, you can apply this iteration to get alpha 2, alpha 3, and so on. Okay? And the second thing to be mindful of is, if you recall, it's like we talked about the issue of round-off error, right? And in particular, one of the dangerous things with round-off error is when you divide, when you take the difference, when you take the difference of 2 numbers which are close to each other. Okay, so you're subtracting 2 nearly equal numbers and then dividing by a small number as well. So this has the effect of potentially introducing a lot of round-off error, right? So it can introduce lots of round-off error. So one needs to be aware of that as well. Okay, so All right, so that's the Newton method and that's the secant method. All right, so now I'm going to write down the algorithm for the Newton and secant methods. And I'm going to break it down. So most of the algorithm is very similar, but there are some instances where they diverge from each other. And in those cases, I'm going to put these curly braces to indicate that there are two cases. All right, so the first case is for the Newton method. So the input is the function, its derivative, the initial point alpha 0, the tolerance to decide when to stop the method, and the maximum number of iterations, and this is for Newton. And then the secant method just requires the function value, two initial guesses, alpha 0, alpha 1, a tolerance, and again the maximum number of iterations. So this is secant. Right, and the output in both cases is alpha n, and the number of iterations you take, which is n. So, all right, so you're going to first initialize the iteration number. So n is going to be 0 for the Newton method, and it's going to be 1 for the secant method, because for the secant method, you're already given alpha 0 and alpha 1. Okay? And then m stop, which is this flag, which indicates whether or not the termination criterion has been satisfied, is set to 0. Okay, so now while n is less than the maximum number of iterations big N, and the termination criterion has not been reached, so m stop is equal to 0. I'm going to sort of increment the iteration number, and then I'm going to update the sort of the next iterate for, or the next guess for alpha. So this again is broken up into two cases, one for Newton and one for secant. So in the Newton method, it's alpha n is equal to alpha n minus 1 minus f evaluated alpha n minus 1 divided by f prime alpha n minus 1. Okay, so that's the Newton method. And then with the secant method, it is again very similar, except that instead of the tangent, instead of the derivative, sorry, you replace it by the slope of the secant line. So that's f alpha n minus 1 minus f alpha n minus 2, alpha n minus 1 minus alpha n minus 2. Okay. And then the next thing now is that we can determine the termination criterion. So with the Newton and secant methods, you don't have a sort of enclosure, you don't have a bounding interval where the root is guaranteed to live in, so you don't have a guaranteed sort of upper bound on the error. So what you do instead is that you look at how much the iterates change by, and when the iterates start sort of stop changing by a large amount, that's one reason to stop, right? So if alpha n minus alpha n minus 1 is less than your tolerance, that's you know, a proxy for the absolute error, right? And the other thing you can do is still do the residual error as before. So f at alpha n, if that is less than the tolerance, if those two conditions are satisfied, then I can set m stop is equal to 1, and then I can end the while loop. Okay. All right, so that's basically the algorithm for the Newton and secant methods. Very, very similar, except for slight differences in the input, in the initialization, and in the update. Okay, but the logical structure is very much the same. Okay, so the next thing we'll talk about is error analysis of both the bisection method and the Newton method. So let me stop here for now.